In this example, we are being asked to compute the magnitude of the resultant force acting on the screw eye and its direction measured clockwise from the positive x-axis. So let's go ahead and draw this figure together. So we're going to have some kind of thing called a screw eye here. This is kind of like a bolt that you can, attach maybe a rope through it of some sort, okay? And we're going to say that right through this bolt, we have the positive x-axis here, okay? And attached to this bolt or this screw eye, we have two, maybe they're ropes, maybe they're wires. In either case, we have two vectors, okay? Acting just like this. So we're going to call this vector over here, it's going to have a magnitude of 2 kips, okay? And it is at a 45-degree angle here. And then the vector to the left is going to have a magnitude of 6 kips, and it is at an angle of 60 degrees measured from the negative x-axis. So this is our system right here, okay? And again, here are our directions. Maybe pause the video and write these down and really think about what we're being asked to do here, okay? So let's go ahead and get started. Under solution, the first thing to notice is the directions do not specify to use either scalar or Cartesian methods, okay? So I personally use scalar notation if the directions do not specify which ones to use. I personally think scalar notation is a little bit more user-friendly. So let's use scalar notation. So I'm just going to say let's use scalar notation since the directions don't specify which one to use. Okay, so remember, scalar notation is the method where you are not using I hat and j hat. Now, the next thing to notice is this figure does not tell you which vector is F1 and which one is F2. It doesn't label them. So if a figure doesn't label the vectors F1 or F2 or F3, then just label them yourselves. Just be clear about it, okay? So I'm going to say, let's call F1 equal to 6 kips and F2 equal the 2 kips. Okay, that way we've labeled them, okay? We've given them names to refer to. So we're going to follow the same process that we saw in the previous example. We're going to resolve each of these vectors into x and y components. Resolve each vector into horizontal, which again, horizontal we normally call x, and vertical, which we normally call y, components. Okay, so let's look at this vector F1 first. Okay, we're going to say investigate. Now, when we investigate F1, you should notice that F1 is pointing in which quadrant? Well, if you project out another little axis here, F1, which is the 6 kips, is in quadrant 3. And it's forming a right triangle right here. Okay? So if you want to, you can draw this out kind of like this. And again, F1 is 6 kips. And we can form our right triangle right here. And so this length is going to be F1x. And then, of course, this length here is representing F1y, and then of course we have the 60-degree angle right here. All right, so how do we get these two components, F1x? Well, if you remember, look back in your notes, F1x is going to be F1 times what? Times the cosine of this 60 degrees. And it's cosine of 60 degrees. Notice it's because the 60 degrees is being referenced from a horizontal axis here, okay? And then you can use your calculator, and of course make sure your calculator is in the correct mode. You want it in degree mode, not radians mode. So of course we're going to have 6 kips times cosine of 60 degrees. And when we punch this through, we should get 3 kips. And again, it's pointing to the left, which means you would either put a negative sign in front of this, indicating that it is pointing to the left, or you could say 3 kips, and then you put a left pointing arrow. And remember, we don't put both of these. You put one or the other, because if you put negative 3 kips and then a left pointing arrow, that's like saying a negative times a negative is a positive, which would imply it's pointing to the right, which it is not. Okay, now let's look at F1y. F1y is going to be F1 times the sine of 60 degrees, and that's going to be negative 6 kips times sine of 60 degrees. And of course you can put that in your calculator and see what 6 times sine of 60 is, and that will be 5.20 kips. Now we'll also have a negative there, and you can say that that's 5.2 kips pointing down. And again, we're in quadrant 3 here with F1, so that means that its x component and its y components are numerically negative. And so that's it. That's F1x and F1y. Now we're going to do the same thing. We're going to say investigate F2. Investigate F2, okay? And so by looking at F2, what do we have? Well, F2 is pointing over here. That's an ugly looking vector. Let me draw it better for us. F2 is pointing here into quadrant 4, and that equals 2 kips. So what are its components? Well, we're going to have an x component here, call this F2x, and then we're going to have a y component here pointing down, F2y, and here's our 45-degree angle, okay? And again, how do I know F2x is pointing to the right and F2y is pointing down? Well, you just look at the direction of F2. Its x component is oriented to the right, and its y component is oriented down, okay? And so in a similar way that we handled F1, we're going to say F2x is 2 kips times the cosine of 45 degrees. And let's see what that ends up being. 2 times cosine 45 is 1.41. And if you want to take it out one more decimal, 1.414 kips. Put those units there. And it's positive, or you could say it's directed to the right, okay? And then we're going to say F2y is 2 kips times the sine of 45 degrees. And that's going to be also 1.414 kips. Now, should we have a negative here? Yes, we should. Quadrant 4 has what sign, S-I-G-N components? Well, quadrant 4 has positive x values but negative y values. So we would put a negative here, or you could say 1.414 kips pointing downwards, okay? So now what we do is we're trying to get the resultant force, right? So the next thing we're going to do is we're going to say the resultant x component is going to be the sum of all of the x components. Now, what do we take as positive? Well, we put a little arrow up here saying to the right is positive, okay? And so this is going to be equal to F1x plus F2x, because again, we have 2 components here. We have 2 forces, each having their own x component. So being very mathematically proper and going one step at a time, F1x, if I scroll on up, was -3 kips. So we're going to say -3 kips. And again, that negative indicates it was pointing to the left. And F2x is going to be plus 1.414 kips. So what do we get here? Well, we should end up getting a negative 1.59 kips. And what does this negative indicate or tell us about our resultant x component? Well, it tells us that it should be pointing to the left. So we're going to say it's 1.59 kips pointing to the left. Okay, again, we did some calculations here. Our resultant x component came out negative, which means it's pointing in the opposite direction of what we called positive. We called things pointing to the right positive. Okay, so that's FRX. And now we're going to do a similar operation on FRY. We're going to say FRY equals the sum of all of the y components. And what do we typically call positive in terms of a y direction? We typically call upwards positive. So that would give us F1y plus F2y. And following a similar format, we're going to say FRY equals, what was F1y from earlier? Let's scroll on up and see. That was -5.2 kips. -5.2 kips. And then what was F2y? F2y was minus 1.414 kips. And so what happens when we combine these two? We get negative 6.614 kips. And what does that negative indicate about our y component of the resultant force? Well, that indicates that FRY is pointing down. So we could say 6.614 kips pointing downward. Okay? And now we're finally going to get to our magnitude of the resultant force. The magnitude of the resultant vector force is going to be obtained from performing a Pythagorean theorem operation. So we're going to say it's equal to the square root of FRX squared plus FRY squared. And that would give us 1.59 kips squared plus, negative, put a negative in there, plus a negative 6.614 kips squared. And again, all that's wrapped up in a square root. So what is this magnitude gonna equal? Well, remember, don't forget, you're squaring these negatives, right? So it is negative 1.59 squared, but you square the negative, so it becomes a net positive. Same thing on the negative 6.614. It becomes a net positive because you're squaring the negative as well. So once I perform this operation, you end up getting a positive value always for the magnitude. So it's positive 6.8, and if you want to take it out a few more decimals, 0.2 kips. Okay. Now, if we want to draw this out, I mean, the problem did not explicitly tell us to draw it out, but I find it very helpful for visualization purposes to draw these things out. So that's what I like to do. I would draw it out XY here, put your coordinate system here, and then we look for FRX is negative 1.59, or it's 1.59 pointing to the left. So here's FRX, and then FRY was a negative 6.614, so that's going to be a bit longer, 6.614. Here, let me just label it FRY. Okay, and then the resultant is gonna be directed at these little projected lines here, right here. And so this is the magnitude of the resultant force, which equals 6.802 kips, okay, in quadrant 3. Does it make sense that we're orienting the resultant in quadrant 3? Absolutely. FRX and FRY were both negative, so that orients us into quadrant 3, okay? We also need the direction of this. Now, if you look back at the original problem statement, look in your notes, it says, what is the direction measured clockwise from the positive x-axis? So what we're really looking for is this angle right here, theta sub r. Okay, now here's where you got to be very, very careful. Okay, if you are going to perform that arctan operation, that is based on right triangle trigonometry. Okay, so let's be very careful here and be very deliberate. Okay, this is FRX. And this is, I'm going to draw this a bit bigger. This is FRY, okay? And here's the magnitude of FR. Now, this angle right here, I'm going to call this phi sub r. You could call it anything. I'm just calling it phi sub r. All right, phi sub r is going to be equal to the arctan of the magnitude of FRY over FRX. Okay, now the reason why this particular angle is the arctan of FRY over FRX is, again, because this is based on right triangle trigonometry. So we are investigating this right triangle here, okay? We're investigating this right triangle. And the tangent of this interior angle, which I just called phi sub r, the tangent of that angle is opposite over adjacent, okay? Opposite over adjacent. So therefore, phi sub r, what I so fondly named phi sub r, will be arctan of opposite over adjacent. And again, make these values positive, okay? The calculator that you use will not understand if you put a negative inside the arctangent. It doesn't understand quadrants. You have to manually think and understand what it means to be in quadrant 1 versus 2 versus 3 versus 4. Okay, so let's compute this. Phi sub r is going to be equal to the arctan of FRY over FRX. So 6.614 kips over 1.59 kips. And let's evaluate that. So 6.614 divided by 1.59, and we get 76.48 degrees. But again, that is this interior angle right here. That's not explicitly what the problem asks you to calculate. The problem asks you to calculate this thing called phi sub r, and it says in the problem statement, referenced from measured counterclockwise. I'm sorry. It says, did it say counterclockwise or clockwise? Say clockwise from the positive x-axis. I'm sorry. Clockwise from the positive x-axis. So back up just a second. Maybe you caught this already in this video. So clockwise from the positive x-axis is actually this direction. Go ahead and make that correction in your notes. There it is. Clockwise. Clockwise is the direction of a clock. Okay, so if we want it clockwise from the positive x-axis, then how do we get that? Well, we say phi sub r is equal to 180 degrees, right? This is 180 degrees minus this little angle right here. So theta sub r is 180 degrees minus phi sub r, okay? And so what do we get when we punch this through? We should get 103.52 degrees. And that is the other part of our answer. So you want to make a summary, and you want to box this in with a straight edge, okay? So your final answer, we say summary, the magnitude of f sub r is equal to 6.802 kips, and then comma theta sub r is 103.52 kips, and box that in with a straight edge. And again, my apologies, I thought about the problem wrong just for a second. It does ask for the angle measured clockwise from the positive x-axis. So maybe you saw me, you detected me drawing that incorrectly earlier in the video. Good for you. And that will conclude this example.